Hello, everyone, and welcome to the talk. I am Max, and this is follow-up for stuff that I started with my dissertation research back in 2022. And as we've got a lot of material to cover today, I hope you'll excuse me if I just dive right in. So as there's a bit of background material, quite a bit of background material to give here, the motivational section of this talk is going to be rather brief. As promised, if you listen to this talk, you will come away knowing, among many other things, an example of a function from the two-adic integers to the five-adic integers, which can be integrated as if it took values in the three-adic integers. Just to be clear, this is unprecedented and kind of insane. In the process of unraveling this mystery, we'll encounter a totally new way of encoding arithmetic and geometric information, specifically information about absolute values of points on algebraic varieties and counting points on algebraic varieties in analytical objects, specifically by using algebras of measures and the algebras on which those said measures act. There will even be connections to arithmetic dynamics. So just as a review, in case you don't already know, here's a brief crash course for you for what a p-adic integer is. As is well known, given a number p greater than or equal to 2, we can write every positive whole number in base p. For example, 5 in base 2 is this. Morally, a p-adic integer is then a number that is allowed to have potentially infinitely many digits in base p, and we can think of these as formal power series in the variable p. And if you're an algebraic type, you can the ring of p-adic integers is canonically isomorphic to the ring of power series in a single variable mod this ideal. And this is the p-adic valuation and the p-adic absolute value. This defines an absolute value on the integers, and which gives us a metric, and the completion of z with respect to this metric gives us the p-adic integers. So now we have the onslaught of notation. I use fractor, font, x, y, z, etc. for p-adic variables because I think it's cool, but it's to distinguish it from other variables. For any integer greater than n greater than or equal to 0, I use this bracket notation to denote the projection of from a p-adic integer to the unique integer in this interval congruent to it mod p to the n. Lambda p is the number of p-adic digits of n. Lambda 2, if you're a computer person, is also known as the number of bits of n. The number of j's is the number of j's in n's p-adic digits. I'll drop the p if there's no confusion. And we define the number of zeros as the total number of digits minus all this number of digits which are not 0. The triple bar is how I write congruence modulo A. Thus, I can write Z congruent to K mod P to the N, like so. And I use Iverson bracket notation for indicator functions. This says that this denotes the function which is 1 if Z is congruent to K mod P to the N, and 0 otherwise. So N0 denotes the non-negative integers, and ZP prime is ZP take away N0. The little DEF over the equality means by definition. Viewing elements of QP as formal Laurent series in the variable p, every p-adic rational number x is uniquely expressible like so for some integer L0. The p-adic fractional part is the canonical projection from QP onto QP mod ZP, and it's given like this. We note that the fractional part is always going to be a p-power denominator rational number in the interval 0, 1, and when equipped with the operation of addition modulo 1, this set becomes a group denoted ZP hat. This is the Pontryagin dual of ZP. The p-adic fractional part is then a homomorphism of abelian groups, where here the congruence mod 1 means that the difference between the two sides is always an integer. Again, viewing the p-adic fractional part as taking values in 0, 1, we can then make sense of a complex exponential of the p-adic fractional part, and we can use this to construct characters of ZP, which are these are continuous group homomorphisms from Z into the circle group, and these are the building blocks of our Fourier analysis. Don't worry, there will be notes along with this talk. You can get them, just note in the chat thread. They should be at the top of the chat thread, or notes to download. It gives everything I've talked about in much greater detail. The talk will also be recorded. So now, just before we go on, there's actually an important technical point. For psychological and aesthetic reasons, no matter what ring we are in, whatever ring, whatever field, whatever, I am going to use complex exponentials to denote roots of unity. There's for important psychological reasons for this, and this can be justified and explained using the theory of embeddings of global fields into their various completions, and everything works out just fine. But I don't really have enough time to explain all the details. Just focus on the formulas. Indeed, one of the big takeaways of all of this talk is going to be that much of what I'm about to show you holds formally. So next, we need to talk about absolute values on rings. Given a ring R, an absolute value on R is a non-negative real valued function satisfying the following properties: positive definiteness, multiplicativity, and the triangle inequality. We say that the absolute value is non-Archimedean if it satisfies the ultrametric inequality, also known as the strong triangle inequality. If it does not satisfy this, we call it an Archimedean absolute value. This should be it's wrong, it should be Archimedean, and the trivial absolute value is defined like so. And if this holds as an inequality, then i.e., if our absolute value is submultiplicative, we call it a norm instead. A valued thing, usually a ring or a field, is a thing equipped with an absolute value. A normed thing is a thing equipped with a norm. Normed things and valued things are automatically metric spaces, with the metric being exactly what you would think it is. A complete valued or normed thing is a valued or normed thing that is complete as a metric space, and another term for a complete normed ring is a Banach ring. Yeah. Now we need to go over a little bit of algebraic number theory. A number field, K, recall, is either Q, the rationals, or a finite degree extension thereof. OK is the ring of integer elements of K. These are the elements of K which are roots of monic polynomials with coefficients in Z. Two absolute values on K are said to be equivalent if the metric spaces they induce on K are homeomorphic. Equivalence of absolute values defines an equivalence relation on the set of absolute values of K, and a place of K is then a specific equivalence class of absolute values. We say a place is Archimedean or non-Archimedean based on whether the absolute values in it are or aren't. And the trivial place is the place corresponding to the trivial absolute value. Absolute values are intimately related to the algebraic structure of our number fields. The classic example of this is Ostrowski's theorem, proved in the early 20th century, which gives a complete list of all of the places of the rationals. Q has one non-Archimedean, aka finite place, for each prime P, corresponding to the p-adic absolute value, and there is also a single infinite place corresponding to the real Archimedean absolute value. In general, a non-Archimedean place of a number field corresponds to a prime ideal in the field's ring of integers, while an Archimedean place corresponds to an embedding of the field in the complex numbers. Given a number field K and a place L, KL denotes the completion of K with respect to the metrics induced by an absolute value in L. By equivalence, this completion is independent of the chosen absolute value. KL is then called a local field. KL bar is the algebraic closure of KL, and KL double bar is the metric completion of KL bar, and yes, sometimes you have to do that. Note, we can also do all of this for certain positive characteristic function fields, and everything I'm about to tell you works for them as well. In general, everything I'm about to apply works for global fields. And CP is the metric completion of the algebraic closure of QP. So now and forever, unless said otherwise, we fix a prime number P and a commutative unital ring R in which P is a unit. Note that this means that R cannot have characteristic P. So now we need to talk about Schwarz-Brouhat functions. The following sets here form a topological base for the ring of p-adic integers. I call these cosets of ZP. Each coset is compact and both open and closed. In particular, these are Clopin sets. We call this the Clopin basis, the basis of Clopin sets. Importantly, since indicator functions take values in 0, 1, and since R is a unital ring, we can view our indicator functions as R-valued maps on ZP. Moreover, by taking R linear combinations of these guys, like so, we get more complex functions. In particular, any R linear combination of finitely many indicator functions of cosets gives us what we call a p-adic Schwarz-Brouhat function, or SB function for short. A general SB function, as said, is going to be an R linear combination of finitely many indicator functions of clopin sets of ZP. The SB functions form an R algebra with scalar multiplication and pointwise addition and multiplication. When R is the completion of a number field at a place L, I speak of the p-ell-adic SB functions, and the p-infinity-adic means that R is either the reals or the complex numbers. So once you have local Schwarz-Brouhat functions, you can define distributions. A p-r-adic distribution is an R linear map from Schwarz-Brouhat functions to R. We write this to denote it, and notation-wise, if we have a Schwarz-Brouhat function f, and a distribution d mu, we write the integral of f d mu to denote the image of f under d mu. The p-adic hard distribution, which I denote dz, is the unique translation invariant distribution, which sends the constant function 1 to 1, and unless stated otherwise, all integrals from here on out are going to be with respect to the hard distribution. Now we need to get topology and continuity involved. Let R be a topological ring. Then every Schwarz-Brouhat function is continuous. It is actually, this is an elementary exercise, and it's a really good one, and it involves using the fact that the base of ZP's topology is clopin. And so because of this, we can take limits of linear combinations of SB functions to obtain continuous functions. So henceforth, we're going to assume R is a metrically complete valued ring. This gives us our important spaces of functions and their duals thereof. CZPR is the Banach ring of continuous p-r-adic functions. The norm is the supremum norm, and just as considering linear functionals on the SB functions gave us distributions, considering linear functionals on the space of continuous functions get us measures. In this case, a p-r-adic measure is a continuous R linear map on the space of continuous p-r-adic functions to R, and the space of all of them is denoted as CZPR prime. Much like with distributions, we denote the action of a measure on a function by an integral. It's also important to note that the space of all measures is a Banach ring under convolution with respect to this total variation norm. I'll remind you what convolutions of measures are in a moment. Also note that the SB functions are dense in the space of continuous functions. Now, Harm measures. It is incredibly important to note that the p-r-adic Har distribution extends uniquely to a p-r-adic measure called the p-r-adic Har measure if and only if P's absolute value in R is greater than or equal to 1. If the reverse is true, then the increasingly small sets will have increasingly large measure, which will result in the measure not being continuous. So from now on, unless stated otherwise, we're going to assume P's absolute value is greater than or equal to 1. And though it is possible to give an axiomatic characterization of the Har measure, for simplicity's sake, we'll define it here by the limit of the following p-adic Riemann sum. And I say that a function is p-r-adically integrable whenever this limit here exists, and of course, where it converges in R. Yeah, this then gives us how to do Fourier transforms. Let arc Cp infinity denote the ring obtained by adjoining to R all p power roots of unity, and let S denote the metric completion of arc Cp infinity. Then the Fourier transform f hat of a continuous p-r-adic function is defined by the limit of the obvious Riemann sum taken in the topology of S. More generally, I say a p-r-adic function f has a Fourier transform f hat from zp hat to S whenever the above limit exists in S. Though I originally wanted to go more in depth about the mechanics of computing Fourier transforms, I had to cut it for time, and so check the note packet for this lecture for lots of details. Henceforth, we will work with a metrically complete, algebraically closed, non-Archimedean, local valued field, big F, of characteristic Q, where Q is a prime not equal to P. So I call this next result the fundamental theorem of p-q-adic analysis. Let f be a p-q-adic function, then the following are equivalent. F is continuous. F is integrable. F hat exists for all t, and F has a Fourier series representation that converges to it uniformly everywhere. This is complete insanity. by analysis standards. And just this, importantly, if we make by making these q-adic continuous functions into a Banach algebra under pointwise multiplication, the Fourier transform is an isometric isomorphism from this Banach algebra onto the Banach algebra C0 of all functions f hat from zp hat to f, which tend to 0 at infinity. And here the star denotes convolution over ZP hat, which is defined like so. The norm on C0 is the supremum norm. Note, I will sometimes drop this and write it as PF when there's no chance of confusion. And in general, when given a sum of this form, it is defined by this limit here, where this sum here is over all t in ZP hat, whose denominators are at most p to the n. Yeah. Also, it's worth mentioning that the fundamental theorem was first established in 1967 by W.M. Shikoff in his PhD dissertation, Non-Archimedean Harmonic Analysis. The theorem attests to the surreal rigidity of p-q-adic functions and is a large part of the reason why p-q-adic analysis of this sort has been basically ignored for over half a century. However, we shall see this conclusion is a bit premature. But to give you an example of how ridiculous this is, in this setting, the only measurable finite set is the empty set, and in particular a function which is 0 at everywhere but a single point is not integrable because it's discontinuous. So after the fundamental theorem, the next most important result is the Parseval-Plancherel identity. This says that for two continuous p-q-adic functions f and g, the integral of the product of fg is equal to the sum of the product of f hat of t and g hat of negative t, where both expressions are evaluated using the topology of f. The Parseval-Plancherel identity is incredibly important because it allows us to give a complete characterization of p-q-adic measures. Namely, every p-q-adic measure, d mu, is of the following form for some unique bounded function mu hat from zp hat to big F, and this function mu hat is called the Fourier-Stieltjes transform of d mu, and it's defined by the image of the associated p-adic unitary character under d mu. The Fourier-Stieltjes transform is then an isometric isomorphism of Banach algebras, mapping the convolution algebra of measures to the pointwise multiplication algebra of bounded functions. And here is the Parseval-Plancherel method for defining the action of the convolution of two measures on a given function. So now we actually get to the meat of the stuff. So the F-series XQP. Letting the number of ones here denote the number of ones digits in a two-adic integer, consider the following formal expression where p and q are, say, distinct prime numbers. I call this an F-series, and this is probably one of the simplest examples. Well, let's make some observations. When z is a non-negative integer, the projection of z mod 2 to the n will be equal to z for all n greater than the number of two-adic digits. Because of this, we can write the following. We split up this sum, and then we get a convergent geometric series. This converges in the real topology, and when we sum it, the result here is a rational number, and therefore a q-adic number. On the other hand, when z is in z2 prime, z has infinitely many digits, and as such, the nth term of x tends to 0 q-adically. And it's a fundamental fact of ultrametric analysis that in a complete non-Archimedean valued field like the q-adic numbers, a series converges if and only if its terms tend to 0 q-adically. This shows that x converges in QQ for all z in z2 prime. The conclusion? From this, we see that the F-series XQP defines a 2 q-adic function provided we sum it in R when z is in n0, and sum it in this should be QQ, not QP, and sum it in QQ when z is in z2 prime. I call this recipe for summing the simple XQP, I call it the simple 2 q-adic frame, and I save and I write it like so to indicate we're using this. When we want to unambiguously distinguish the function from the formal power series, we will write this here. And so we can now characterize XQP like so. And in fact, using these, it's the unique function satisfying these functional equations subject to the rising continuity condition here, meaning that the value of f of z mod 2 to the n converges q-adically to f of z as n goes to infinity. Using these functional equations, we can compute the values of x recursively. This can be used to show that despite being rising continuous, x is not actually continuous in the classical sense. Indeed, we have the following. This is equal to what x is of 0 is, and x of 2 to the n is this. Since 2 to the n tends to 0 two-adically, if this function was continuous, the limit as n goes to infinity of this would tend q-adically to that. However, because p and q are distinct primes, this won't ever converge. It'll just cycle around the unit circle indefinitely. So the limit here fails, and thus we don't have continuity. According to this, the fundamental theorem would suggest that xqp f2q ought not to have a Fourier series. However, as I showed in my dissertation, that isn't the case. To see how, we'll need some notation. Let q be an algebraic number. Then I define the function pi q hat, like so, where negative v2 of t is the exponent of 2 in the denominator of t. As part of my dissertation, I proved the following. Let p and q be non-zero elements of a number field k, and suppose there are places LP, LQ of k with associated absolute values so that the following inequalities hold. Then our F series converges to a rising continuous function from Z2 to KLQ. And here we sum this by summing it in the topology of KLQ when Z is in Z2 prime, and the topology of KLP when Z is in N0. Let's call this recipe of summation F. Then letting xqp hat be the following function, where v2 of 0 is defined to be positive infinity, we then have that this is a Fourier transform of xqf in the sense that the Fourier series this generates converges to the F series, provided we sum it using the recipe dictated by F. The moral of this result is that even though x is not even though x isn't continuous, we can still compute its Fourier transform, but at the cost of having to use a frame to sum the ensuing Fourier series. Indeed, because xqp is not continuous, the Riemann sum here, whose limit gives us the Fourier transform, does not, in general, converge q-adically. This makes us wonder, in what sense is the previous formula I gave for x hat equal to its Fourier integral? The answer is that xqp is acting as a measure here, and that xqp hat is its Fourier Stieltjes transform. To show this rigorously, it helps to have the p-adic Wiener algebras on hand. Here, let F be a metrically complete, algebraically closed valued field. We'll allow it to be Archimedean if necessary. And then the Wiener algebra, WZP big F, is the set of all p f-adic functions so that F has a uniformly convergent Fourier series if big F is non-Archimedean, and F has an absolutely convergent Fourier series if big F is Archimedean. This is then a Banach algebra with respect to the following norm, and where f hat is the Fourier transform of f. The algebra operation is pointwise function multiplication, and Young's convolution inequality shows that this is indeed a Banach algebra. I write W of ZPF prime to denote the continuous dual of the Wiener algebra, which is the set, which in this case is the set of all measures on the Wiener algebra. Note that the terms Wiener measure and Wiener distribution already refer to two very important, completely unrelated objects in the studies of stochastic processes and statistics, respectively. Also, as defined, and this is quite important, when F is a q-adic field and P and Q are distinct, then the p-q-adic Wiener algebra is not just isomorphic to the p-q-adic continuous functions, these are actually the same set. So now using Wiener algebras, we can interpret xqp as a measure. In order to do this, all we need is for there to be a place L of k so that xpq hat is ell-adically bounded uniformly over a z2 hat. This then allows us to use our Parseval-Plancherel formula to define xqp dz as a measure on the 2 ell-adic Wiener algebra. In fact, with a little more work, we can make the condition for x being a measure even more specific. Uh, we note this very important generating function identity. It is then easy to show that the locally constant function q to the number of ones in z mod 2 to the n has as its Fourier transform the following. Here, 1, 0 is the indicator function of 0 in z2 hat, and note this makes a 1, 0, 1 periodic function. Um, and so when we compute this, a simple modification then gives the following two formula for the Fourier transform of this function. And note, the answer depends on whether or not q plus 1 is equal to 2p. Letting n tend to infinity, we get the following theorem. Uh, let k, p, and q be as given in the previous theorem, and suppose there is a non-trivial place L of k with an associated absolute value, so that q plus 1 over 2p has an ell-adic absolute value less than 1. Then we get the following limit. Moreover, the Parseval-Plancherel expression then defines a measure qp of z dz on the 2L-adic Wiener algebra. If, in addition, L is Archimedean and q plus 1 over 2p has an ell-adic absolute value less than 1/2, then both the F-series xqp and its Fourier series representation converge absolutely in KL double bar and therefore define an element of the 2L-adic Wiener algebra. So the conclusion is that the analytic properties of xqp and its Fourier transform are sensitive to the equation q plus 1 equals 2p. As this is an algebraic variety in two variables, I call this equation the breakdown variety of xqp. The most obvious way this sensitivity manifests is in the fact that we get two different formulas for xqp hat depending on whether or not q and p lie in the breakdown variety. In addition, the Wiener algebras on which xqp acts as a measure correspond to those places L for which q plus 1 over 2p has an ell-adic absolute value less than 1. Also, the Archimedean Wiener algebras containing xqp correspond to the infinite places L for which q plus 1 over 2p has an ell-adic absolute value less than 1/2. Just to hammer home how weird all this is, consider the following example with the F-series x52. Using the simple 2-5-adic frame, we can realize x52 is a rising continuous 5-adic valued function of a 2-adic integer variable. Here, though, since q plus 1 over 2p is 3/2, which has a 3-adic absolute value of 1/3, the limit of this Fourier integral converges 3-adically to x52's Fourier transform. So this means that if we use our Parseval-Plancherel formula, we can realize x52 as a 2-3-adic measure. Furthermore, if we identify the limit of the integral here with the Fourier integral of x52, we then have that this integral converges 3-adically to x52 hat, despite being 5-adically valued. Thus, we have 3-adically integrated a 5-adic valued function. Note, this is like only the second weirdest thing we'll be seeing today. So, as the saying goes, all magic comes with a price, and the same is true here. Noting the following Fourier identity, we see that when p and q lie in x's breakdown variety, this term over here, the series term, dies. When p and q are distinct primes, we then get the follow in the breakdown variety, and we have this equation. Note that what we get here converges to 0 as n goes to infinity with respect to this 2q-adic simple 2q-adic frame. That is, this thing converges to 0 in the reals when z is a non-negative rational integer, and this thing converges q-adically to 0 when z is any other 2-adic integer. As the Fourier coefficients of this series are q-adically bounded uniformly with respect to t, the Parseval-Plancherel relation gives us a 2q-adic measure. In classical analysis, this sort of thing would suggest perhaps that the measure we're working with is the 0 measure. However, it isn't. The Fourier-Stieltjes transform, it's not identically 0. I first came across measures of this type in my dissertation. I call them degenerate measures. An F2q degenerate measure is a 2q-adic measure d mu such that the Fourier series generated by mu hat converges to 0 with respect to F2q. That is, it converges to 0 in the complex numbers if z is a non-negative rational integer, and converges to 0 in CQ if z is in z2 prime. The existence of these degenerate measures has a profound implication for our Fourier analysis. Letting mu hat be the Fourier-Stieltjes transform of any f2q degenerate measure, observe that both xpq hat and xpq hat plus mu are Fourier transforms of xqp, in the sense that they both generate Fourier series which converge to xqp with respect to this frame. So, unlike in classical analysis, the Fourier transform of xqp is not unique. Rather, it's only well-defined modulo an arbitrary f2q degenerate measure. In my dissertation, I called this phenomenon quasi-integrability because it implies that while we can make sense of uh, this integral here of xqp as the value of some measure at t equals 0, the value of the Fourier-Stieltjes transform of some measure at t equals 0, the problem is that the choice of the measure is not unique. Indeed, it is a subspace of the vector space of two q-adic measures, and so losing uniqueness in this way is the price that we have to pay in order to use frames to expand the class of meaningfully integrable two q-adic functions beyond what the fundamental theorem says we can already integrate. So now that we've seen the basic example, before we generalize, we need to talk about frames. When working with XQP, we were able to choose a single metric completion of the field K in order to make sense of X as a function from Z2 to the completion of our field. However, for more general F series, it's not going to be possible that, and even if we pick a weird frame, that we're going to be able to fit all of the values our function spits out into a single field. And here's a simple example of this. Consider the p-adic F series, X defined by this, where P, Q, and D are non-zero, non-unit integers, with P and Q being distinct primes. Now, if Z is in N0, then this is going to converge in R, and it's going to be a rational number. Meanwhile, if Z is in Z3 prime, the series will converge p-adically if Z has infinitely many ones digits, q-adically if Z has infinitely many twos digits, both p-adically and q-adically if Z has infinitely many ones and twos digits, infinity-adically, that is in the reals, whenever this lim sup condition is satisfied. In this way, we have an example of an object that's too big to be viewed as taking values in just one local field. While having multiple different fields is perfectly common in algebraic geometry, doing hard analysis in a situation like this is, as far as I know of, totally unheard of, at least until now. So to define a frame, intuitively, a frame is just a device for recording unusual recipes for interpreting sequences of functions as convergent. So for us, the following definition will suffice. Let R be a commutative unitary ring, and let abs R denote the set of absolute values of R. Let X be a set, and let D of F be a subset of X. An R frame on X is a map F from df to the absolute values of R, which sends each X in df to this given absolute value. I write Rfx to denote the metric completion of R with respect to this absolute value, and d of f is called the domain of f. To make sense of functions with this, we're going to just union together all the different completions that f of R that f spits out, and we're going to call this I of f, the image of f. So this holds anything that is the completion of R with respect to some absolute value specified by f. I then say a function from df to if is compatible with f whenever f of x is in the completion of R specified by the frame at x for all x in big F's domain. C of f then denotes the set of all compatible functions. This ends up being an R algebra under pointwise operations and scalar multiplication. A sequence of compatible functions converges to a compatible function with respect to f whenever the limits occur pointwise. That is, fn of x converges to f of x in the topology in the absolute value specified by big F of x for all x in the domain of big F, and I write this like so. And before it's proceeding, it's worth mentioning that in general, an R frame on X is a map from the domain of from its domain to the set of ring norms on R and convergence with respect to a frame. Actually, it's ring norms of the algebra of R-valued functions on X, and convergence with respect to a frame ends up being a metrizable, locally convex topology with relatively nice properties. So, having covered the introductory example of XQP, now let's get a bit more general. Let P be an integer greater than or equal to 2, and let the AJs be indeterminates, and let R be a commutative unital ring in which P is a unit. Then a p-adic F series over R is a function X from the p-adic integers to the ring of formal power series in the A's with coefficients in R of the following shape. Here, the number of k's is the number of k's digits in base P, and the fn's are a sequence of p-r-adic Schwarz-Brouhat functions. I say X is a simple F series when Fn is equal to C for all n and z for some constant C in our ring, and when R contains all p power roots of unity, I say X is a foliated F series when the Fn's have the following form, where the b hats are some constants and the epsilon n's are these following functions, whereas always we are using complex exponential notation for roots of unity in R. Also of interest are, as we will see, are F series of either of the following two forms, where P is a polynomial over R. Cases where P is a rational function may also be of interest. I will refer to the AKs as the parameters of our F series, and though we define these as indeterminates, we will in practice treat them as elements of R, and which can be made rigorous, note, by quotienting the ring of power series here by the specified ideals. And so for the rest of this talk, we'll just assume that the AKs are elements of R unless specified otherwise. One of my main results of my dissertation was the following. Let P be a prime number, let K be a global field of characteristic non-equal to P, let AJ and BJs be constants in K, with none of the H's being 0. Then there exists a unique function X from N0 to K, satisfying the following system of functional equations. Suppose further, there is a K-frame F on ZP, so that this limit is F convergent for all Z and ZP. Then the limit defines a compatible function with our frame, and moreover, X is the unique compatible function satisfying this functional equation subject to this rising continuity condition. Moreover, defining the functions alpha x, beta x, gamma x, a hat x from zp hat to algebraic closure of K by the following formulas. The function x hat from zp hat to K defined by this formula if alpha x of 0 is 1, and this formula if alpha x of 0 is not 1, then generates a Fourier series, which is F convergent to X. Uh, uh, Moreover, X admits, in fact, we get this by summing the Fourier series. X admits an F conversion representation as a foliated p-adic F series, and there exists at least one place L of K, so that which gives a realization of X as a measure on the p-ell-adic Wiener algebra. I describe all of this by saying that X is quasi-integrable with respect to F. And just as with the previous example, if we pick a degenerate measure, then we get another Fourier transform of our function. Just as XQP was sensitive to Q plus 1 equals 2P, X is sensitive to the equation alpha X of 0 equals 1, which I call the breakdown variety of X. And this expression on the left here is the breakdown polynomial. Yeah. So just like with XQP, we can relate the p-ell-adic Wiener algebras on which X acts as a measure to the places L where its breakdown polynomial has absolute values less than 1. So these are the following theorem. Let everything be as in the quasi-integrability theorem, and suppose there is a place L of K with an associated absolute value such that the breakdown polynomial has an ell-adic absolute value less than 1. Then the following limit converges ell-adically, and the Parseval-Planck-Charel construction gives a realization of X as a measure on the p-ell-adic Wiener algebra. If in addition, L is Archimedean and the average of the AJs has ell-adic absolute value less than 1/2, then both the foliated F series for X and its Fourier series representation are absolutely convergent in KL double bar and therefore define an element of the p-ell-adic Wiener algebra. This result is very useful because it yields an easy proof of a special case of one of F series' most important properties, that they form algebras under pointwise multiplication. As the pointwise product of two measures or distributions is not guaranteed to be a measure or a distribution, this is somewhat surprising. Indeed, in the easy Archimedean case, if x and y are two F-series over K that belong to a p-adic Wiener algebra for some Archimedean place L, the pointwise product of x and y will also be in that algebra because that's what it means to be in an algebra. However, it turns out that even without the help of the Wiener algebras, the pointwise product of pretty much any two F-series of the type described in the previous theorem will also have an F-convergent Fourier transform, provided the two F-series are compatible with a common frame and that they don't cancel each other out. I'm currently polishing a paper on this for publication at a later date. Although actually getting to the details is quite quite laborious. The algorithm for doing so is really straightforward, and so this is a very nice algorithm for computing the Fourier transform of either the product of two F series or the powers of a given F series. I'm going to show the latter case. We're going to show you how to derive the Fourier transform for the powers of x, provided that we avoid the troublesome breakdown variety. So proceeding formally, letting x be a foliated F-series characterized by these functional equations, the trick is to use these guys in conjunction with the following string of integral identities. And so setting f to be the product of x to the n and a p-adic character, we get this computation. So here we use this partition of unity, then we apply the functional equations, and then we use the binomial theorem to expand this into sum of powers of x. So this gets us this. And here, letting x hat star k of t denote the Fourier integral of x to the k, and letting x0 z denote the constant function 1, whose Fourier transform is 1, 0, we have the following recurrence relation. Pulling out the k, the n equals n term gives us the following. Here, note that this sum right here is independent of k equals n. It only depends on the values of k strictly less than n. And the key thing to note is that since t is in zp hat, and since every non-zero element of zp hat has a p-adic absolute value greater than or equal to 1, multiplying t by p decreases t's absolute value. It reduces the 1 power of p in the denominator of t. Because of this, the level sets of inputs of the x's on the right-hand side have absolute values which are 1 power of p lower than the absolute value of t on the left-hand side. So suppose that we have shown that x hat star k is defined for k equals 0 up to k equals p minus 1. Then letting t have an p-adic absolute value of p, note that pt is then an integer. Since the x star k hats are functions on zp hat, they are 1 periodic, and we get that x hat star k of pt is equal to x hat star k of 0 when t has absolute value p. Because of this, we get the following expression. And what this shows us is that the values of x hat star n at t in the level set of absolute value p are completely determined by the values of the other x hat star k's at 0. So proceeding by induction on the absolute value of t, once we know what the values of the x hat star n's are on the level set of absolute value p to the m, we can then use them in conjunction with the recurrence relation to compute the values of x hat star n of t on the level set of absolute value p to the m plus 1. In this way, knowing the values of the x hat stars at 0 determines all the values of x hat star n. Setting t equals 0, we then get the following, and this leaves us with two cases. If alpha n of 0 is not equal to 1, we can solve for x star n hat, and going to be in terms of the x hat star k's at 0 for k less than n. In this case, we see that x hat star n is completely determined by x hat star 0 through x hat star n minus 1, and we're done. By induction, we see that this will occur precisely when alpha k of 0, this guy, is not equal to 1 for any k from 1 up to n. Because of this, I call alpha k equals 0 the kth breakdown variety of x, and the expression here on the left is the kth breakdown polynomial. But what happens if alpha n of 0 equals 1? To make sense of this, we need some definitions. First, given a p-adic F series X, a frame F with respect to which X is compatible, and an integer K greater than or equal to 1, I say that a measure d mu is a realization of X to the K with respect to F whenever a mu hat generates a Fourier series that is F convergent to X to the K for all Z in F's domain. I write I write R Fn of X to denote the set of all realizations X to the n of X n. And it's important to note here that d mu being a realization of X to the K is formally equivalent to saying that X to the K is the radon-Nicodemus derivative of the measure d mu. Second, given a frame F, I say a measure d mu is F degenerate whenever the Fourier series generated by mu hat is F convergent to 0 for all Z in the domain of F. Now we make some observations. For a fixed K-frame F, the set of all F degenerate measures is a vector space over K. We just add them together and we get another degenerate measure. Moreover, given two different realizations of Xn with respect to a specific frame, their difference is necessarily a degenerate measure. This shows that the nth realization space of X is an affine vector space. That is, it's a coset of the space of degenerate measures. And so we can write it like that. So to better understand the alpha n of 0 equals 1 case, let's consider a more concrete example. Specifically xq2, where q is not equal to 3. This F-series kth breakdown variety is this equation here. And as the first breakdown variety is satisfied only when q equals 3, then we have that X admits the following Fourier transform. Remember, though, that this formula is not necessarily unique. We can add any F2Q degenerate measures Fourier-Stieltjes transform to this guy, and the result will be another perfectly valued formula for a Fourier transform of xq2. In this way, note that knowing the value of xq2 hat of 0 is then equivalent to having specified a particular realization of xq2. Our recursive equation for x hat star n reduces to the following in this particular case when n is equal to 2. Setting t equals 0, we can express x hat star 2 as a rational function in q. The pole of the function at q equals 3 comes from the first breakdown variety. Likewise, the poles at plus or minus root 7 come from the second breakdown variety. So as long as q squared is not 7, our choice of realization of xq2 will uniquely determine a realization of xq2 squared. In this case, we see that the second realization space of xq2 has the same dimension as the first realization space. However, if q squared is equal to 7, then we must choose a value for x squared's Fourier transform at 0. And in this case, the degree of freedom has gone up by 1. And so the dimension of the second realization space, when q is plus or minus root 7, is 1 more than that of the first realization space. Indeed, we can explicitly solve for the Fourier transform of x root 7 2 squared for all non-zero t, and we get the following formula, which clearly shows the dependence on the freely choosable value of here, which is the integral of x root 7 2 squared. We then get a second degree of freedom by adding on a multiple of an arbitrary f2q degenerate measure. Thus, it seems that the dimension of x's nth realization space increases based on the number of k from 1 to n for which x's parameters satisfy its kth breakdown variety. Note that while it's clear that the dimension of something is going up, formulating this rigorously is a bit of a thorny issue at the moment due to the fact that there's no reason to expect the space of f degenerate measures to be finite dimensional. Figuring out the right formalism for this is on my to-do list, and once that is done, we can start figuring out how to reverse this paradigm and use F theories to study algebraic varieties. Also, just between you and me, the reason I haven't worked this out rigorously yet is because I only noticed this dimension increasing phenomenon earlier this month when I was writing up the first draft of this presentation. I hope that gives you an inkling of how rapidly this new subject of mine is developing. So now I have to make a confession. This is the part of the talk where I have to apologize for having hidden a gigantic ulterior motive from everyone. Namely, everything we've discussed so far has been in service of my full frontal assault on the infamous Collatz conjecture, also known as the 3n plus 1 problem. For the 0.01% of you that haven't heard of it, in terms of the shortened Collatz map T3, this is the conjecture that T3 eventually iterates every positive integer to 1. For an odd integer q, we can greater than or equal to 1, we can similarly consider the shortened qx plus 1 map, tq, and it's important to note that this can be extended from a map on z to a map on the two adic integers. Just as a refresher, recall that a periodic point of a map is a point that the map eventually iterates back to itself. For a map on the integers, a divergent point is an input whose iterations under the map are unbounded. The Collatz conjecture implies, but is not equivalent to, the statement that T3 has no divergent points in N0. Meanwhile, it is conjectured that the set of T5 divergent points in N0 has a natural density of 1, which in essence, almost every non-negative integer should be iterated to infinity by T5. The smallest one, which is suspected to go to infinity, is 7. None of these statements have been proven. Now, consider the two-adic F-series chi-q. In my dissertation, I showed that this series is summable with respect to the 2q-adic frame and defines the unique 2q-adic rising continuous solution of the following functional equations. The connection between F-series like chi-q and arithmetic dynamical systems like TQ comes from the first big result of my dissertation, the correspondence principle. This says that the rational periodic points of TQ on the two-adic integers are precisely the rational q-adic integer values attained by chi-q over the rational two-adic integers. Note that this also subsumes all of the periodic points of TQ in the ordinary integers. Moreover, if chi-q of z is a rational integer at an irrational two-adic integer input, then x is a divergent point of tq and z. This proof, by the way, is completely non-constructive. It follows from the basic properties of dynamical systems on the integers. And I conjecture that the converse of this guy is true, although proving it appears to be difficult. I also conjecture that the divergent points of TQ are all points in the image of chi-q, at which chi-q's fiber contains infinitely many elements. Rather than obsessing over improvements of quantitative knowledge about the dynamics of Collatz type maps, my research focuses on studying F-series and the surrounding analytic phenomena in the hopes that better understanding them will eventually yield meaningful advances in our knowledge of Collatz type arithmetic dynamical systems, while also perhaps contributing new tools to non-Archimedean algebraic and arithmetic geometry along the way. Another way of formulating the fiber conjecture is that the divergent points of TQ, if they exist, are necessarily points at which the graph of chi-q has a self-intersection. To that end, one of my long-term goals is to try and find a way of making sense of chi-q as a curve, in the hopes that techniques of arithmetic and algebraic geometry can be brought to bear on studying it, and by extension, the dynamics of TQ. Now, while it might seem preposterous to treat a function out of Z2 as a curve, this is actually just a very minor modification to an already well-known construction, the so-called de Rham series. And yes, this is a de Rham cohomology de Rham. Let MD be a complete metric space, let B be an integer greater than or equal to 2, and let the H's be contraction mappings on M. It can be shown that for any infinite sequence of A's in 0 through B minus 1, the infinite composition sequence of HA0, of HA1, of yada, 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 will be a constant function whose output is completely determined by the choice of ANs. Next, using base B, we can uniquely represent every real number in the unit interval, like so, for some sequence of integers a n of x. When all this is said and done, the de Rham curve generated by the hj's is the map C from the unit interval to M, which to each x in the unit interval outputs the constant to which the composition sequence from the h specified by x's base b digits converges. Just here are some examples. Now, not only can we realize chi-q or any simple or foliated F-series as very nearly being a de Rham curve, but the method of constructing de Rham curves is pretty much identical to how I originally arrived at them. Letting K be a global field, let X be a p-adic foliated F-series satisfying functional equations of the following shape, where the AJs are non-zero elements of K, which are not units of the rings of integers of K. This is crucial because that means that for each j, there is some place Lj of k at which aj's absolute value is less than 1, which makes this map hj as defined into a contraction on klj. It can be shown that x of z is the function which, to every p-adic integer z, outputs the fixed point of the composition sequence of the HJs specified by a p-adic integer z's digits. And this is how I originally constructed these guys. I considered these maps and arbitrary compositions of them. If z is in zp prime, then there is a j between 1 and p minus 1, so that z has infinitely many j's digits. And in this case, the composition sequence here will converge to a limit in klj. On the other hand, if z is an n0, we have that the z's digits are eventually all 0, and thus that the composition sequence will converge to a limit in kl0. This observation also then tells us how to construct a frame compatible with x. So even though my approach uses the p-adic integers, while de Rham used the unit interval, the underlying idea is the same. We both constructed our curves by considering a map from the set of all infinite sequences in n distinct symbols to the set of all composition sequences of n maps. Indeed, using this map eta2, it gives us a continuous, surjective but not injective map from the two adics integers to the unit interval. We can precompose chi-q with an inverse of eta2 to realize chi-q as a de Rham curve, C, from the unit interval to zq. In this sense, everything can be unified by thinking of all these curves as maps out of profinite spaces. Indeed, it turns out that the underlying idea in all of this is mapping really from one profinite space to another. Letting p and q be distinct primes, we get these natural continuous maps psi qp from the p-adic integers to the q-adic integers like so. I call these the space change maps, and they satisfy many desirable properties. They are uniformly continuous with a Holder exponent. Their injectivity and surjectivity depend on P and Q, and just like F-series, the space change maps can be given as the unique rising continuous solutions to certain systems of affine linear functional equations. In fact, this shows that the space change maps are just another example of F-series. Both, and here's something really cool, both quasi-integrability, that is, the existence of a Fourier transform, and rising continuity are preserved by precomposition by a space change map. Even better, we can think of that map eta2, which embeds the z2 in the unit interval, as a space change map from the two adic integers to the reals. And what this suggests, and because it satisfies this functional equation, and this suggests that there ought to be a way to unify all of this in the context of maps out of appropriately chosen categories of profinite spaces, and thereby realize F-series as direct image functors. Perhaps the methods of Clausen and Scholl's condensed mathematics might be of use in helping to flesh out our understanding of the geometry of an F-series as a curve, and through that give better insight into the Collatz conjecture. And that's the end. So I'm going to do unmuting so we can add, now we have questions, and comments, and popsicles. So let's see here. Let's do stop share and meeting. So ask everyone to unmute, and if you want to talk, go ahead. Anybody? Ben Dover asked, will this form an abelian category? I have no idea. And it's one of the things I'm going to be working at, because eventually I'm just an analyst trying to make sense of all of this and translating this into modern algebraic geometry terminology is just one of my big hopes, because I do feel like there's a lot here. So let me just go ask a question. So Brian asked, why is the set of degenerate measures a vector space? Oh, that's easy. So this goes back to frames. In the idea of a frame, remember, we're looking at everything pointwise. A degenerate measure is one such that when we generate a Fourier series using it, the result is 0 everywhere. If we have two degenerate measures, then their sum, well, that the Fourier series generated by the sum of two things is the same thing as the sum of the Fourier series they generate. So if mu hat generates a Fourier series that converges everywhere with respect to our frame, then adding that to another series with that property will give us a degenerate measure. But the fun thing is, remember, the way a frame is designed, we're working with a given based ring, or in this case, a field. So as an example, the simple q-adic frame, it assigns the real topology to n0, and it assigns the q-adic topology to all the other two-adic numbers. This is a Q frame, a rational frame. So that means everything we get, the space of compatible functions, it's an algebra over Q. In a frame, actually, let me just go back to let me go back to the screen share. Where is it? No, it's here. It's here. Let me just go back to that and just it's one of the it's built in. I'm honestly, it amazed me myself when it was this part what I was struggling with. So we say that the compatible functions are so that everything happens pointwise. Here, R is this is a completion of f of x. And so as a result, it still has a structure as an R algebra. When you complete a ring or a field to get a larger field, everything in that completion can still be multiplied by numbers of the original field. That's what makes it work here. But let me just see what any other questions we had. More chat. Boop. And zoom. Okay, where is let's stop the share and go to questions. Okay, so if anyone just want to talk out loud, I've asked everyone to unmute. If you don't want to, we have another message. No, it's a vector space because we can multiply any one of them by a constant k. For example, if I have a measure which converges with respect to a certain frame, if we multiply it by any rational number, because the frame works with completions, everything works out quite nicely. It's all being done pointwise over k. Does that clear up the question? It's because it's both the sums and the fact that we can multiply the measure by any. But the whole point is if a sequence converges with respect to a frame, then we can multiply it by any constant in the base field without losing a convergence. Could you resend the notes packet? Yes, I can. One moment. The note package is boop. Let me share it right here. I am sharing the note package here. And notes talk. The notes have been shared again. Yeah. So again, the point is that we can multiply them by scalars because F convergence is unchanged by, indeed, if we have an F convergence sequence, we can add any scalar in the underlying field or multiply by any scalar in the underlying field without losing everything, without losing any of the topology. It's also a lot clearer when you do this in the context of locally convex spaces. I explained this in, I think it's my episode 7 video where I talk about frames. But the main thing that matters is that because we get these, it's technically an algebra under pointwise operations. That's why it works. Okay, any other questions?
These like XPQ, these things there was some equation related to it. You called it a breakdown variety,
yeah.
But it's, I mean, is it an actual algebraic variety in some sense?
It's an actual algebraic variety. If I may just go back to where we were, screen share and actually, no, let's do this. So that's that. Sharing screen. I want to share the it is an actual algebraic variety. Though in this case, again, remember when I originally defined an F series, the definition that I gave was that we're treating it as it's a ring of formal power series. And so then these constants here, the A's, and likewise, in this case, the B's, we can think of these as formal quantities. And then as a result, when we take this thing, when A, J's, and B, J's are formal indeterminates, the breakdown variety ends up being this thing. In one of the themes of my research is that rather than focusing on a single Collatz type map, I want to focus on families of them. A simple example is the shortened QX plus 1 maps. In that case, we get q plus 1 over 2p is the variety. P is fixed if we want. Actually, in this case, p ends up being equal to 2. But here, what this says is that as long as we treat the AJs as indeterminates, we then get the following equation, which it's an honest to goodness algebraic variety. I'm pretty sure that the correct formalism that will end up being necessary here is some kind of moduli space, or possibly maybe a scheme of a family of F series, and then we can get individual ones by taking a quotient and local. I didn't yet. What term is localizing? We can take it by taking a quotient and evaluating them to be specific constants. So in this case, a higher order breakdown variety, this ends up being, again, it's an algebraic variety. Because all of this can be done formally, we don't need to think of these as fixed constants, but they're indeterminates. And yes, this is an algebraic variety. Another cool thing is that there's this interaction. If you allow the p to change, you end up getting it ends up becoming a projective variety because you can change things by comparing it's the AJ's, right? Where did I put it? The AJ's here you can actually see that there's a bit of a projective thing going on, because even though it looks like there's a negative a0, when you multiply this and add everything up, it ends up that the a0 and the ak and have the correct exponents. And in this case, so for example, any birational map of a0 and ak over a0, that will then give us another F series. And so we can study, and one of the things I want to do is study F series, say up to birational equivalences of their parameters, and then figure out how to start classifying things and grouping them. Indeed, right here, what this shows is that as long as you change a0 and ak, the ratio is what all that matters, and so that means we have a projective variety. Good question. Anyone else?
Yeah, well, maybe if there's no one else, I'll maybe just ask. I had another question. Well, I have two other questions actually. So one was, you had some comment about you said the only measurable set was the empty set.
The only finite set in the p-q-adic context, the only measurable finite set is the empty set. By that, what I mean is that a function that is non-zero at only finitely many points will not be integrable unless it's the zero function.
Sorry, what's the measure space here?
In this case here, it's the p-q-adic Harm measure. So I'll get it. Technically, the measure space construction is a bit problematic. Just if you go into non-Archimedean functional analysis, there's an accessible entry-level explanation of it will be in the appendix of Shikoff's Ultrametric Calculus textbook, where he talks about integration on compact ultrametric spaces. The fundamental the way you do it in ultrametric analysis is because the traditional construction using subadditivity ends up being nasty. You start with a ring of, meaning that a set which is closed under complex and finite unions, and the Clopin basis ends up being a ring of sets. And then we define a measure as a distribution, first as a distribution, meaning a linear functional on the Schwarz-Bruhat space, and then we get a measure by taking a completion. And in this case, if we take the completion with respect to the q-adic absolute value, and if we're working let's consider the rational coefficients, and we're going to take the completion with respect to the q-adic absolute value, where q is a prime distinct from p, then the result will give us the space of continuous p-q-adic functions, and we then define measures as the continuous dual of C, ZP, QQ. And in that context, it turns out that we get a Harm measure. And in one way to compute it is just literally by doing this integral. And it turns out
so this is supposed to it just ends up being the Harm measure on the p-adics?
The way I like to think about it is that as long as we're working over the Schwarz-Bruhat function, we don't need to worry about convergence because everything is finite, only finitely many sums, finitely many terms, etc. Where things get interesting is when we pick a particular absolute value, take a completion. So as an example, let's just start with the rational valued Schwarz-Bruhat functions on VP. If we take the completion of that ring with respect to the real supremum norm, we'll end up getting the space of real valued functions, which can be integrated with respect to the real valued p-adic Haar measure. However, if we complete with respect to a q-adic supremum norm, we'll end up getting a space of functions that can be integrated with the q-adic valued Haar measure. So it's different completions of this Haar distribution. And it turns out that when you complete using the p-adic absolute value, you don't get something continuous because this right here, as n goes to infinity, this set intuitively becomes small, but this number p-adically would become huge, which means that the p-adic distribution does not extend to a bounded linear map, p-adic valued map on the space of p-adic continuous functions. However, when we consider this q-adically, this is going to be bounded as n goes to infinity, and it turns out that we can get we end up getting this measure. And the weird part is when you go through this, it turns out that if you define measurable set as a set whose indicator function is measurable, it turns out that measurability is that since the integrable functions are the continuous functions, the only measurable sets are those whose indicator sets are continuous. In this case, we know that these are a Clopin basis for the topology, so the indicator function of a set of this shape is always going to be measurable. But you can't take finite unions and intersections of these guys and get finite sets that are not empty. And so what that says is that when you use this PQ-adic integral to define your measure, any set of finitely many points that's not empty is going to be non-measurable because its indicator function is not PQ-adically continuous.
Okay, so the measure space is the p-adic numbers, but this whatever Haar distribution thing is not related to the actual the actual Haar measure.
Yeah, the construction is using the functional analysis approach, where we define measures as linear functionals on appropriately defined spaces of test functions. The standard approach where you use a sigma algebra of sets does not really produce nice results in non-Archimedean analysis. And that Chekhov's ultrametric calculus textbook, the appendix, I believe, it gives an example of where if you just try and use the classical sigma algebra approach, you end up getting just nonsense where everything ends up being degenerate in a frustrating way.
I guess that's kind of weird though, because like
it's weird.
Just for like regular measure theory of just the p-adic numbers, the Haar measure, like that all works fine.
Yeah, and that because what it shows is what all that's and really it shows the massive effect. What you're changing is the field that everything is happening in. As long as we let our measures be real valued or complex valued, everything works out the way we want it to. But just to give you an example of one of the fundamental problems, when you're working in PQ-adic analysis, there is no triangle inequality for integrals. The integral of an absolute value can be smaller than the absolute value of an integral. In fact, I can easily pick a function such that the integral of the absolute value is either equal to the absolute value of the integral, smaller than it, or larger than it. It's completely useless, and that's fundamental. That's what the problem is that it boils down to that sizes don't add up, which is really what the intuition behind a non-Archimedean metric space is. It's one where distances don't add up. And that makes measure theory behave very strangely.
Okay, I think I get it a little more now.
Yeah. Well, these are all excellent questions. Anyone else? If not, then I think this is it for today. And I'm glad. Oh, should I have questions? I see people in the chat. What is CP? CP is we can say it's the complex p-adic numbers, but it is the metric completion of the algebraic closure of the p-adic of the p-adic numbers. So so people forget about this, but Q, when you go from Q to the complex numbers, what you're first doing is you're going from the Q to the reals, and then from the reals to the complexes. And the reason why complex analysis is amazing is because the complex numbers happen to be have a two-dimensional degree extension of the real numbers. However, in an ultrametric field, this falls apart. Indeed, the metric completion of the algebraic closure of the field of q-adic numbers is not locally compact. Why? Okay, yeah. So so in that case, in this just generally true that algebra that the specific term is the CP lacks the property of spherical completeness. Whereas the ordinary complex numbers does have it. We have another one. So let's see. Another question is, why does Geo asks, why does this setting end up being ideal to study the 3x plus 1 problem? One of the, that's just a really good question. When I wrote that correspondence principle that I mentioned, which I said that it tells us that we can understand Collatz types of problems dynamics by studying the value distribution of the chi-q function. In the proof, you have to use the fact that the branches of the Collatz map, the 3x plus 1 branch and the x over 2 branch, those define homeomorphisms of both the 2-adic numbers and the 3-adic numbers, and you have to use them both. That is to say, these maps, we can't just capture all of the information by studying solely with respect to a single prime p. We have to study both of them at once. And one of the broad themes of my research is that we can take these formal identities and study them from the perspective of any metric completion of whatever field or ring we're working over. And indeed, one of the things I want to work on is a theory of functions from the adels to the adels. And that just figuring out how to do this. In particular, as I mentioned there, I think we might be able to end up doing a homological algebra by studying, for example, if we take a given F series and we precompose it with a space change map. And then doing this, we'll find some way to geometrize these curves. And then if we can do things like compute their fundamental group or find out how many rational points they have or integer points, that would allow us to actually say whether to determine whether or not a Collatz type map has divergent points, or to determine how many rational points, periodic points it has, etc. So next question, Brian asks, the completed tensor product of the p-adic integers with the q-adic integers is 0 in condensed mathematics. How does your formalism sidestep this issue? I have no idea because I'm just an analyst with a terminal analysis brain. The main thing that I have some colleagues who are working into it. The thing that what I'm doing right now is I'm trying to figure out the correct context for these F series. And with the observations I pointed out there at the end, rather than just working directly with p-adics and q-adics, what I want to do is use these F series as an intermediary between them. As example, one of these weird ideas that how do you think homological algebra will work in your setting? I don't know, partially because right now I'm still at the level of trying to figure out what the right spaces are. It just is a simple parallel. Back in the mid 20th century, when people were trying to figure out how to do geometry over a p-adic field for the first time, there was a fundamental problem, is that when you are considering an analytic function in a p-adic context, if you expand the analytic function in a power series at a given point, the radius of that expansion doesn't change if you move the point. Analytic continuation in the naive sense doesn't work in a p-adic context. And this means that you can't use the Weierstrass theory of germs and stuff to define sheaves of analytic functions in a p-adic context, and this created huge problems. And there have been multiple attempts to fix it over the past half century or so. First with rigid analysis, which uses limits of rational functions, and then with Berkovich spaces, which replaces p-adic affine space with spaces of semi-norms that end up being pathwise Hausdorff and pathwise arcwise connected. And in this case, I think it's similar to what's happening before. As we saw in classical PQ-adic analysis, that what Shikov did, they assumed that all of the functions we needed to be working with were continuous. But it turns out, just like with classically analytic functions in a p-adic context, that ends up being too much of a demand. When you weaken to rising continuity in F-series, things become more workable. And right now, I'm just trying to figure out what the right spaces are. What are the categories of F-series going to look like? What are the morphisms? All of this is just completely unknown because no one's ever studied any of this stuff before. We need to figure out the patterns to then to figure out how to abstract it. So yeah, so yes, the homological algebra. That's one of the reasons why I have hopes in the advanced mathematics. There might be some way of, if we can abstract F series and view them as basically as functors out of profinite spaces, that might then give us a way of doing geometry. The again, for what properties are looking for these categories, I don't know. I'm not an algebraist. I don't even know just the definition of a sheaf gives me a headache. It's one of the reasons why I'm looking for researchers to help me so that I can flesh these things out. So a p-adic analog of the Hadamard factorization theorem, yes, there is a p-adic Weierstrass. No, the Hadamard factorization theorem, that I don't know. There is a p-adic Weierstrass factorization theorem, though. So the radon-Nicodemus connection derivative, okay. So that is, I can explain a little bit about that. So it turns out, quite amusingly, that when you're taking the radon-Nicodemus derivative, what you want to do for that is you take the integral of a function over a set, and then you divide by the integral of the set with respect to the measure that you're differentiating against. Amazingly, it turns out that let me put it right here. Here, let's let no. That's where did I put it? It's here. Yes, here. So just ignore the right hand side, and just look at this. If I have a measure d mu and I consider this sum right here, this nth partial sum, this is basically equal. This is equal to the image of a. This is equal to the measure of a radius 2 to the n neighborhood of the q-adic integer 0 divided under mu divided by the measure of that neighborhood. So this right here, this expression is precisely equal to the formal difference quotient that you would take the limit of in order to use the Lebesgue differentiation theorem. And so in this case, the act of summing this infinite series, it's easily and immediately shown to be formally equivalent to taking a radon-Nicodemus derivative. I explained this connection in detail. I believe it's in episode 5 of my series. Maybe it's the one about it's the one where it's the episode's called "Where No Wiener Has Gone Before." Just Google PQ-adic analysis and a wiener and a YouTube video search, and you'll get an explanation. It covers the connection to the radon-Nicodemus differentiation. Formally equivalent, yes, actually, better. Is there a formal equivalence? Absolutely. So in blah, in Fallen's real analysis book, when he presents the radon-Nicodemus differentiation theorem and just the Lebesgue differentiation theorem, he introduces the Hardy-Littlewood maximal functions. The Hardy-Littlewood maximal function, that construction, if you replace a open ball with the p-adic version of it, it directly becomes this formula. I actually show that process in the video that I mentioned. Yeah. And let's see here. So, uh, so here I'm again the problem with radon. If one other person asks is what details on the radon-Nicodemus thing. So as I said, the problem with non-Archimedean measure theory is that instead of using sigma algebras, we do everything in terms of duality theory, where we use defined measures as the continuous linear functionals on appropriate spaces of test functions. So in this case, I don't really worry about the distinction between a radon measure or a Borel measure, blah, 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 because my measures are specifically concrete things that come out by saying it's a continuous linear functional on a space, particular type of space. And I'm going to be blunt here. Non-Archimedean functional analysis and measure theory becomes impossibly awful to read. It gets very abstract very quickly because of all of the technical conditions that are needed to make things work. However, by a minor miracle, p-adic analysis ends up being a nice enough of a setting that you can do things explicitly like this without having to work on so many different technical conditions that it just becomes almost impossible to read. Um, excellent, excellent, excellent. Um, yeah. Anyone else? I just also my Discord chat. My if you go to I have my server that you can access that on my Discord profile, and from there I can give you a link to my research server. Also, oh yeah, is there any specific results related to the Collatz conjecture that you have obtained or believe are obtainable using the F series? I believe that it may be at the moment. I believe that it may be possible to rule out to prove or disprove the existence of divergent points if we can figure out how to properly define the geometry of F series. But I won't lie, at the moment, this is all still very conjectural. But what makes me excited about it is because no one's ever done anything like this. And the fact that there's so much of it, and I just keep looking and it just keeps coming out, I it it I for me, it feels less likely that this is all just some weird accident than that I've actually found something significant. I thought there's just too much here to be just a coincidence. And what sources of inspiration do you have for my work? Um, I just like doing computations. I like playing around. I like experimenting and seeing where things go. Ultimately, I could say that all of this ended up happening because first I was playing around with compositions of maps, and then I took a limit and saw that the limit existed p-adically. Later, for the F series, I was just playing around with summing identities, and I found identities that no one had ever apparently computed before. And with them, I'm able to prove stuff. I believe the example I gave is here. Yes, this identity right here, which I derived. I was working on this back in I think 2020, 2021, where and just if you just notice when q plus 1 over 2p is equal to 1, that dies, and then this thing goes to 0 using the frame. It's that and indeed the notion of the frame I originally developed was just a shorthand so that I didn't have to keep specifying the weird convergent recipe. And then it turned out that the notion of frames ended up being exactly what I needed to deal with a much larger class of Collatz types maps than I had originally been set out to study. So quasi-integrability, it's a bit technical, but the idea is that I say that a function is quasi-integrable if there is a measure such that the Fourier-Stieltjes transform of the measure generates a Fourier series which converges to our function with respect to a certain frame. So and to go to this, I would say that X, in this theorem, XQP, this thing is quasi-integrable because this formula, when you sum it, the Fourier series it generates, the result will converge to this expression, provided you use a frame. A quasi-integrable function is a function that can be realized as a measure, such that the Fourier transform of the measure generates a series that sums to the original function, or formally, it's a function which is formally the radon-Nicodemus derivative of a measure. And so other inspirations, I happen to think this stuff is neat. And that's for me, it's just no one's ever seen it. I enjoy doing the computations and I like figuring out where things go. I've just been following my nose. And in that respect, it's actually contributed a great deal to my sense of imposter syndrome because I don't feel like I've made any great discoveries or anything. I haven't worked to create something rather like I say like a Grothendieck or a Scholz or whatever. I've just been lucky that I happened that the thing I was playing around with ended up being this bottomless pit of new findings. Yes, I know the hallmark of a good theory is that can be used to solve problems in other places, and the honest truth is I just don't know about what's the extent of what's possible at the moment. I'm trying to bring order to the new world that I've discovered so that we can begin figuring out what to do with it. Uh, as My name is Mr. Siegel, not Mr. Zhang. But anyhow, but yeah, and so right now, one of my goals is to once I understand this and figure out what the right context is, we can start putting an application to it. As I said with this talk, if we can use F series to detect count points on algebraic varieties, if I just once I establish proving that correspondence in full, we can then start doing that to do geometry things. And one of my collaborators suggested that my methods might work for what were they called again? Um, the sequence involving ones and twos. It was covered by a schizophrenic, began with a K, and there's this conjecture about the density of them or whatever. It's a self-referential sequence, and one of my colleagues thinks that my method would be able to tackle that. But right now, at just the moment, I'm just trying to figure out what's possible, and I think that's fun. And so, yeah, I'm going to call it a night for now. I'll be available to talk, but for the time being, thank you for coming, and I hope you enjoyed it. Bye. And we have to end it. How do we end it? How do we end it? How do we end it? How do we where's the recording? Stop recording. There we go. Bye.